what we discussed last time. We talked about the operator product expansion. We talked about the state operator map. We described the operator product expansion. We talked about how the word identities involving charge currents capture a particular term in the operator product expansion of charge currents and other operators. And we also described how those word identities could be used to relate, or how contour integrals could be used to relate terms in the operator product expansion between the commutes corresponding to charges and the commutation relations between these charges, from which it followed that the algebra of charges was completely captured in the structure of poles in the operator product expansion between corresponding charges. At the end of the last class, we also started to discuss the operator product expansion, the singular terms of the operator product expansion of the stress tensor correlator. Though we also talked about this, we talked about word identities for translational invariance, stress tensor. And at the end of the last class, we started to discuss word identities, the operator product expansion for the stress tensor, the stress tensor with itself. Many people after the class told me that they didn't understand what we said about the TTOP. So as promised in the last class, we go through that again. Let's start the next one. So you remember that we've got TZZ, which we decided to call T, TZ bar, Z bar, which we decided to call T. What do we know about TZZ and TZZ bar? You remember that we understood from momentum conservation. Do you remember that we deduced that ZZ bar was 0 in insertions and correlation was 0, at least there are no other operators inserted. We deduced that it was 0 just from the requirement of invariance under conformal transformations. Okay, and then from the requirement that T was a conserved stress tensor, which followed from our notes of procedure, we derived also that TZZ was analytic and TZ bar Z bar was anti-analytic. So we decided to call T ZZ T and TZ bar Z bar T bar. T is an analytic function, T bar is an anti-analytic function, at least away from insertions of other operators. And okay, so we are. Now we wanted to try to understand the operator product expansion between the operator product expansion between T and itself. Okay, and this is how we proceeded. So I'll just go through it more slowly, and you tell me if it makes sense. Okay. So what you want to do is compute T of Z, T of W. Okay. We want to compute T of Z, T of W. Now, T had holomorphic scaling dimension 2. Okay? Which, we will understand this statement more formally later in this lecture, next lecture. But intuitively is the statement that it transforms under scaling transformations, like 1 over Z squared. Okay? Where does that come from? That comes, for instance, from the fact that there are two Z indices. Under diffeomorphisms. So it transforms under diffeomorphisms. Okay? Just like anything but two lower Z indices does. So in particular, it transforms under the diffeomorphism corresponding to a scale transformation, which is Z goes to lambda Z. Okay? Like 1 over lambda squared. Okay? So it's that simple fact that we're talking about. That's what I mean by having holomorphic weight 2. It transforms under the Z under diffeomorphisms corresponding to scale transformations like 1 over Z squared. Okay? Actually, scale transformations are that combined with a particular while transformation. The while transformation of rescaling. But the theory is invariant under while transformations, and the stress tensor is, at least under these constant while transformations, is exactly invariant. So it transforms under combined operations of this diffeomorphism and that Weyl transformation, just like 1 over z squared. As I said, we will understand this statement in a much deeper way by the end of this class or by the next class. But at the moment, you understand it intuitively enough to be able to use it. Okay. So, we have this and this. The next left-hand side is a holomorphic dimension 4. So now I'm going to stop saying holomorphic dimension. Every time I say dimension, I mean holomorphic dimension. Okay. So, what could it be? Well, the operator product expansion tells us that it's some operator. That's fine. It's some operator, let's assume there are no other operators nearby. So it's some operator inserted, let's say a W. Okay? So some O inserted a W. But that's nice, but it's not enough. We want to know why. Okay? The operator in general could be very complicated. The left-hand side depends on both Z and W. Okay? The left-hand side depends on both Z and W. Okay? And so, if you put some O here, it could be in general a function of Z and W. What I'm going to do is to Taylor expand this operator about the point W. Okay? So I'm going, in the language of the operator product expansion, we have a disk which, at the center of which is W, we've got some Z. And there are no other operators inserted in this disk, which is centered at W, and is at least as large as the distance between W and W. Once we have that, we are allowed to use this operator. Good. So I'm going to take this operator, whatever it is, and Taylor expand it in O minus W. However, when I say Taylor expand it, I'm speaking figuratively because there may be singularities in the expansion. Typically, when you bring two operators together, there are singularities. As we've already seen, by the way, with X and X. You remember, we brought X and X together and there was a logarithmic singularity. Okay? We will see this more and more as we go. Okay? Now, because all operators in a conformal field theory are operators of definite holomorphic dimension. Okay? There's a basis. You can always choose a basis of operators with definite dimension. Okay? We can always use this basis to do our expansion. How do I know we can always choose a basis of operators with definite dimension? This follows from the state operator. Because there's a one-to-one correspondence between operators and states. Now, remember that under the state operator map, okay, the energies of states looked at on the cylinder map to the scaling dimensions of the operators. But looked at wherever. How did we see that? It's because time translations of the cylinder became, under the conformal transformation, scale transformations on R2. Okay? So, how an insertion of the operator changed under scale transformations mapped to how the state evolved under time transformations. And so, given that we know that there is a basis of states in any quantum mechanical system with definite energies, we also know that there is basis of operators with definite energies. Okay? Is this clear? So, we're going to use this basis to do this expansion. Because this basis of operators has definite scaling dimensions. Okay? Because this basis of operators has definite scaling dimensions, whatever appears on the right-hand side can be expanded sort of in the schematic sense, O and W by Z minus W to the power alpha. Okay? Let me write this out. Z minus W to the power alpha up here because most of them will be positive. Now, what can we say about these alpha m's? Firstly, alpha m's had better be either 0, positive integers, or negative integers. Okay? Alpha m's had better be whole number. Why? You see, this thing is representing what happens when you take t near to w. Now you have to get a definite answer. But if alpha m was, let's say, square root, was half, then you have two different answers depending on which branch of the function you use. But that makes no sense because inserting t here and t there gives you some particular operator. There should be no ambiguity. Now the way I'm saying it is that if I do this, I've got my w inserted here, and I take z around w. I continuously do that, and I come back to my. I should come back to the same operator because you're doing the same insertion. It's a well-defined insertion of operators within a path integral. But if I had some fractional power here, I wouldn't come back to the same value. I would come back up to a phase, which would somehow say that the insertions of these operators are ambiguous up to phase. Now, as again we will see as we go along, it is sometimes interesting, useful to deal with bits of operators that do have these so-called monodromies around each other in the study of conformity. But the final physical operator, the one that you actually deal with, the one whose correlation functions, which are well-defined operators in the theory, cannot have this problem. You cannot have a monodromy as you take one physical operator around the other. You can in your head, in little mathematical constructions that make up part of the operator, but not in the final physical operator. Okay? This is important to keep in mind. It's a basic consistency requirement of the operator spectrum of your theory. The operator insertions are well defined, and so these things have to be. This is probably sometimes called the property of relative locality. Okay, that the spectrum of operators has to be such that operators are relatively local with the spectrum.
Relating locality.
It's a name. Forget the name if you don't think it. Okay, it's a name you didn't count. Okay. Yeah.
What if your Hamiltonian cylinder has no integral eigenvalue?
Yes, it doesn't matter. You see, we're not saying that every operator dimension here is positive. It has no integral eigenvalue. No, it has to, because the stress tensor is. Okay, and all its descendants. Okay, there's dz or dt and so on. And actually, as we will see as we go along, in two-dimensional conformity theory, the only things that appear on the right-hand side of the stress tensor, TTOP, are the stress tensor and its descendants. Okay, so there is a universal sector of the Hilbert space, or every conformity theory. And this thing is made up only in terms of that. Okay? Good. By the way, this happens in no other dimension. The TTOP in conformal field theories in higher in three dimensions, 4 dimensions, does not have only T's on its right hand side.
From the unicity it should be closed. This TTOP, the closure property.
You can't derive too powerful a constraint from general principles, which is not true in either 2 dimensions. Okay? Why should it be closed from unitary? You can do T and produce something else.
It's taking O type of operator, if it's non-zero, then those can appear.
Those can appear and do appear in n equals 4 angles.
Frequent function.
In n equals 4 angles, a weak coupling TTO is not zero for many operators. Okay? It has to do. I'll explain much of this as we go. But okay. At the moment, we're not assuming anything. Whatever it is. Okay? But we've concluded that these alpha n's are integers. Just in general. Then we're using, as I said in the last lecture, we use one more property, again, that we will see, again, at the end of this lecture or the next lecture. Okay? We use one more property that, again, we will see. We will be able to prove. Which is that in the unitary conformal field theory, all operator dimensions are either 0 or positive. Moreover, the only 0-dimension operators are the identity operators. Yeah, is the identity. Okay? This restricts how large the singularity. The maximum singularity can be here for alpha m can be -4. Okay? And if you have a -4, the operator that occurs on top of it is identity. Okay? So we'll allow for that possibility. We'll allow for identity, but identity we don't want. Right? It's just there. Identity can be multiplied by number. It's identity. If we call that number, whatever it is, we call it c by 2. Z minus w to the 4. Now, the next possible singularity is the cubic singularity. Okay. Now, if you have a cubic singularity, we could have had O3 of W by Z minus W cubed. Okay? We could have had O3 of W by Z minus W cubed. Where O3 of W is just some normal routine operator. Okay. Remember, these are statements within insertions of correlation. So now, suppose this was the case. I now will argue that O3 has to be 0. Okay? Suppose this was the case. Then I want to try to understand what I can say about doing the operator product expansion the reverse way. Suppose I do the OP centered around Z rather than about W. Okay? So I'm in a situation where there's a big enough disk so that whether you choose the center at Z or you choose the center at W, there are no other operators in that. Okay? Clearly there's such a situation, so let's work in that situation. In that situation we have to get consistency. What can we say? Okay? So clearly it must be the case just by symmetry because there's no difference between W and Z, they're just blind labels. C of Z, P of W equals C by 2 by Z minus, I would write this as W minus Z 4 plus O3 of W by W minus Z cube. 3 of Z by 2 by W minus Z cube. What? DW. Thank you. Okay, but now, we've got this disk and we've got some other insertion points, and imagine some correlation function. Okay? One case here, in one case here, I've got a correlation function with O3 inserted at Z. In the other case, I've got the correlation function with O3 inserted at W. Correlation function is some function of this object. Okay? I want to look at what the difference between the correlation functions is. Okay? I want to look at what the difference between the correlation functions is. For that, I want to move this insertion to the same point. But a correlation function is just a function. You move to Z to W, so you can go from one point to the other by Taylor expansion. There are no other insertions nearby, so there are no singularities in the Taylor expansion. Okay? So, we could take, for instance, this guy here. We can take, for instance, this guy and Taylor expand it. Okay? So, this guy is O3 of W plus Z minus W O3 of O3 prime of W. That's del W O3. Okay? Some of you might, who worry about such things, might be worrying, can you just do Taylor expansions on operators like this? Remember, we're only Taylor expanding correlation functions. It's a function we're Taylor expanding. It's no issue. Okay? We do this. Okay. Now, the main point is that while we get a difference, right, because it's Taylor expansion, the difference is only at 1 over W minus Z, the whole thing squared. We get a difference up to two things, up to sign, and the fact that we got the Taylor expansion changes things at order 1 over Z minus W squared. But we want to compare these two functions. These two functions have to be the same. If they're the same, all their singularities are the same. So the 1 over Z minus W, the whole thing cube singularity has to be the same. And it looks good until you remember that here we have Z minus W, the whole thing cube. Here you have W minus Z, the whole thing cube. So these two are not the same. So what we've got is a contradiction, because we've got a particular correlation function. We look at two different ways of expanding the same correlation function. And we conclude that the 1 over Z minus W cubed singularity in these two different ways of expanding the same correlation function is different, which is impossible. Is this clear? Okay? Roughly speaking, what we've said is that we cannot have odd powers because we've got symmetry between the two T's. But that's very rough because we soon get an odd power. Okay? We soon get an odd power and we will see how it's consistent with the correct way of thinking rather than the soft way of thinking.
Basically, lower even power had identity as the.
And identity which had no tail exactly and correctly said. Yeah. So, had this, Mangesh's point is that had this point here, this object here, had an operator which had something at z here and something at w here and something at z here, then there would have been a difference already at order at this one. Now Taylor expansion would have got the leading singularities here to agree, but it would have given differences at order 1 over z minus w cube, which might have been compensated by this. But since this kind of identity does not have a position label, these two just exactly agree with each other. So the first difference occurs here, and because it's an odd power, that differences at leading order cannot be compensated for by anything else. Is this totally clear? So in this OP, O3 must match. That's the conclusion. Is this totally clear? Okay. Correct.
So 1 by z minus w square will give some extension to compensate 1 minus z.
Exactly. We'll see that in detail just now. Okay. Now what about O2? Could we have O2 of w by z minus w the whole thing squared? And here we could have O2 of z by w minus z the whole thing squared. Well, there are two different ways of expanding the same correlation function. Do they give the same answer? This guy and this guy don't give exactly the same answer. They give the same answer at 1 over z minus w the whole thing squared. They don't give the same answer at 1 over z minus w order. But that's not enough to say O2 must be 0. Because we've not finished looking at the terms of in the expansion. Okay? If anything, if there's a difference at 1 over z minus w order, that can be compensated for by what appears in the 1 over z minus w order in the expansion. I will call this 2O2 just for fun, because it will be convenient. So this is so far consistent. Now let me add class O1 of w by z minus w, and also then class O1 of z by w. Now if everything is consistent, it must be that up to terms that are regular, and so could be accounted for by the terms that we have here. These two are the same insertions. What was the rule? Once we have an effective operator here, we just Taylor expand to check whether these two OPs are the same. You remember where that rule came from? I was thinking within correlators. But once we have that in our head, we can just perform naive manipulations. Okay? So let me check whether these two are the same or not up to regular terms. Okay? How do I do that? Let me take this and change every operator insertion point to w. So this is equal to c by w minus z to the whole thing to 4 plus 2 O2 of w by w minus z squared plus 2 del so 2 z minus w over w minus z the whole thing squared del w O2 okay minus and then the next term of the Taylor expansion will make it regular. We ignore such terms. Okay, so I just expanded this to first. Now to what order will I have to expand this? To 0th order. The next term of the Taylor expansion will make it regular. Okay, so plus O1 of w by w minus z. Okay, now we cancel a factor of w minus z here and then make that minus because that was a z minus w. Okay? On the other hand, here what we have is just O1 W. These two have to be the same. So what do we conclude? We conclude that 2 O1 of W must be equal to 2 del W O2. Right? Because this plus this is equal to this. Where did I mess up? This was a Z minus W. That's what it is.
No, that's
I'm sorry. This W is. I messed up and put it where I put my hand. This has to be equal to this plus this. So this you can write in terms of W minus Z up to a minus sign. Okay? So minus 2 del W2 plus O1W has to be equal to minus O1W, which implies this. Is this clear? Okay? So consistency of the OP, of two different ways of doing the same OP, tells us that O2 and O1 cannot be independent. That whatever O1 was simply del W O2. Is this clear? Was this completely clear?
Sir?
Yes.
Did you get the 2 from?
Where did I get the 2 from? This 2 came because we had it here. And this 2 came because we had one term here and minus the same term. Okay? So minus 2 of this object plus 1 of this object has to be equal to minus of this object. So minus 2 of this object has to be equal to minus 2 of that object. So 2 times first object is 2 times. Clear?
At this order, generally, there can be more than one term, which is considered a topic dimension.
Oh yeah, there could be more than one term. So at the moment, all we have seen is that, in fact, holomorphic dimension 2 is what's supported. So we related everything in terms of O2.
Yeah.
There could be anything. However, we're now going to come to a very general, we determine O2 now from the following slide. Again, for any operator in the world, P of W times operator of Z is equal to ideal W. T of Z times operator of W is del Z O of W by Z minus W. Okay, there could be higher singularities, there could be lower singularities, but the pole term in the operator product expansion between P and any operator, any local operator in the world is this. That's the claim.
What we mean by del Z on O of W?
What? I need del W and over W. Thank you. Okay? Where does this come from? You see, what physical input could give you this?
P is the generator of translation.
T is the generator of translations. We have already shown that the generator of any symmetry acting on any operator acts such that the pole in that OP is the change of that operator under the transformation generated by the current. P is the generator of translations. Under translations, how does any operator in the world change? Changes by derivative. Because that's what a translation does, moves. Okay? So it's merely a matter of tracking through signs. You know, whether our conventions for T are such that you should get plus derivative or minus derivative. Okay? And I haven't really told you what T was, so we choose our convention so that we get plus derivative. Okay. Yeah? So this you can take as a defining characteristic of the stress tensor of the generator of the stress tensor. By the way, note from here already we see again that T has holomorphic dimension 2 because we've got one derivative and one z times. Okay, so now T is a particular operator. So while on general grounds we don't know anything else about it, we know that its whole term must give you del W of T. Now look at this object. It very nicely gives you del W of something. So that something must be T. Something must be T up to something that has no derivative. But the only operator in the world that has no derivative is the identity operator. Because fields at different points are just different objects. Inserting different values of fields here, or inserting fields there, is different. Only way you can get an operator that's translationally invariant. And again, we will show this very rigorously, but it's obvious. It's intuitive. Is the identity operator. So, because it's correlation function, if it's translationally invariant, what does it mean? It means its correlation functions don't depend on where you insert it. Which is basically well, all these more or less clear things we will also demonstrate rigorously. Just once we get a bit. Definitely by the end. Okay, anyway. So it's clear, right? So you might have wondered about integration constants in this relation, but there's no such thing. The only integration constant ambiguity is with identity. And identity comes with the wrong dimension. Now, had we been in a theory where there was a mass scale, let's say you deform the conformality theory with a mass parameter, you could have got identity with a power of m squared. That would have made up the dimensions. Okay? But we're not in a theory with mass scale. We've got scale invariance. So we've got nothing to soak up the dimensions. Identity cannot appear. Okay? And therefore, O2 is equal to T. And we conclude that the TTOP, T of Z, T of W, is equal to C by 2, Z minus W over 4 plus 2T of W by Z minus W squared plus del W T by Z minus W. Plus regular. Okay. Any questions or comments about this? Is it clear this time out?
If Z minus W raised to 4 hadn't come with identity, it would have come with some other operator, then its Taylor expansion could have affected the first pole and
all kinds of things could have changed if there had been no identity.
In that case, all kinds of powers should have been right?
What? Exactly. If you allow negative dimensions, you could allow higher significance. Yeah, so, if you give up some of the assumptions, you can question a lot of things. But let's work with this at least. Within the framework of unitary conformity brings. Yes.
Also from state operator correspondence, if I calculate this effective state corresponding to TZTW and evolve it backwards, it seems like this is equivalent to one single effective operator insertion.
Say that again, sorry.
So TZTW from state operator correspondence will look like a single operator insertion.
Yes, with some single operator, expanding operator. It's a single operator, but nobody's told you that it's a single operator of particular energy, particular scaling dimension. It's not. Linear combination of operators, various scaling dimensions. This is our expansion. Okay, excellent. Now that we have the TTOP, we also, if you remember, had in the last class the generators of conformal transformations. Okay, suppose you've got a conformal transformation generated by Z goes to Z plus, okay, let's call it Z is equal to Z prime plus epsilon n Z prime to the power n. We looked at these conformal transformations briefly in the last class, and you remember that their generators were just Z to the power n T. You remember we worked this out using the Noether procedure last class. Okay? These conformal, these conformal generators, the charges corresponding to these conformal transformations have a name. They call it LN. Okay. Right? They call it LN. Okay? They call Virasoro generators. So what are Virasoro generators? They're the charges corresponding to the conserved currents Z to the power n times t. Is this clear? Okay? Is this clear? Now, even before working on one example, I'm going to very quickly work out the algebra of the Virasoro generators. Yes.
When you say it's a charge, what are you integrating over? Like, what's the spatial size you have to use?
What is the space you're integrating?
Yeah.
Integrating J dot n over slices of constant radial time. It's an operator at some fixed time. Fixed time is fixed radius. Okay? But we know that J dot n is simply Jz dz plus the anti-analytic part. Everything we do with the analytic sector goes as a counterpart. We just, okay? Excellent. So, let us make the definition more precise. The definition we will make more precise is the following. Let us take P of Z. Okay. Let us take T of Z and expand it as sum over n ln by Z. Okay? But n plus n plus. Yeah.
Is it EZ, Z raised to n?
Yeah, let me just make sure that let me make sure. Okay, sorry. This is actually my definition. I'm going to have to translate it to which one it is. Okay. Okay. Okay, let me make this definition and we will see what these charges generate.
When you mode expand this piece, like we'll say derivatives of the Z equals Z. So in this case, we will identify the LN, the Virasoro generators. So shouldn't that have Z n plus 1, like del Z?
Okay, hang on for a minute. This is my definition. We'll see how the ln acts on any operator. Okay, let's see how an ln acts on an operator to tell you exactly which of the coordinate transformations it did. Okay. Just what was L0? L0 should have been scale transformation. Yeah, I got that one. They say L0 was scale transformations, and that was epsilon of Z goes like Z. I was saying that, yeah, it was L n is like Z to the power n plus 1. That's why this is right. So the ln is the thing that the charge corresponding to the following conformal transformation. The conformal transformation generated by Z to the power n. Or the ln is the charge corresponding to the coordinate change. Z goes to Z plus Z to the power n plus 1. Okay, that's the notation. Okay? Great. I think Okay, great. So these ln's here are a basis of the charges that generate the various conformal transformations. Okay, and I am going to compute their commutation rates. First, let me invert this thing. What is ln? Just by using Cauchy's theorem. ln is equal to 1 by 2 pi I z to the power n plus 1 times z. Okay. This makes it clear that this is consistent with this. Because this is the integral, this is equal to 1 by 2 pi I jz dz, where jz is equal to z to the power n plus 1 dz. Is this clear? Okay? And therefore ln is the charge generated by this current, and we know that the charge generated by this current is the local charge for a thing coordinate change z goes to z plus n. Z to pi n plus 1 as we worked out in the last class. Is this totally clear? Sorry for having got the n plus 1 wrong, but led to confusion. Now this is correct. Okay. So this is what ln is. Great. So now what we want to do is to compute the commutation relation between ln and ln. That's what we want to do. We want to compute ln and ln commutate. But we understood last class how to do such calculations. Okay? I'll just remind you because you may not yet be used to this manipulation. The idea was we did ln with blue. And now we're going to try to do things including the plus sign and minus sign with 2 lines. Okay? So we did lm with red. Okay? Minus the other way around. That was equal to circling around this point and then contour integrating the result by the contour deformation. Because everyone, this minus the other guy was equal to this. This minus the guy with the blue inside, okay, was equal to this. Okay? And therefore, close the contour, blah, blah, blah. Okay. So what we get?
This definition was given so that you get the correct conserved charges corresponding to the transformation.
I want to label the conserved charges.
Corresponding to each transformation.
To each transformation like this. So I want to label the charge corresponding to this transformation, but up to some 2 pi i's. By definition is fixing the normalizations.
So that definition, it's a scalar transformation.
Are you wondering about the 2 pi i's or the set of the i's?
Definition.
No, the definition has 2 parts. There's a normalization and there's the norm.
No, what I think is the definition was designed so that you get this right. That's how it was.
Yeah, this is the definition, and now we interpret it. Okay? Because this definition is true, we use Cauchy's theorem to get ln. Then we notice that ln is the integral over a current. But the current is precisely the generator of the coordinate transformations. Z goes to z plus z to the pi n plus 1. And then, if you are asking about 1 over 2 pi i's, Noether's theorem doesn't tell you the normalization. We choose a normalization. Okay? So that's convention. So basically this expansion fixes our conventions. There's physics in it, which is ln's generate these coordinate changes. Z goes to z plus z to pi n plus 1. But with what's normalization factor? That's convention. Okay? So now let's try to do this correctly. So we have 1 over 2 pi I times 1 over 2 pi because of the 2 ln's. Then we have this contour integral. This contour integral of ln around ln. How does that contour integral go? It goes like this. We've got z to the pi plus 1 we've got w to the power m plus 1. And then we've got tz, tw. And we're supposed to contour integrate this z around w. What do we pick up in the process? We pick up only the poles. Okay? What do we pick up in the process? We pick up only the poles. So let's do that. Poles in what? In z approaching w, in z minus w. Both these guys run over minus infinity to plus infinity. So they have singular terms at 0. We don't care about those singular terms. We're looking at the local pole as z goes around w. The only possible origin of such a pole is singularities in the OP. Okay? So we can write this as z. So we've got these factors which we keep, and we've got z to the power n plus 1, w to the power n plus 1, and then we use the OP. C by 2, z minus w, the whole thing to the 4, plus 2t of w by w minus z, the whole thing square, z minus w, whole thing square, plus t of w, del w of t, z minus w, plus regular terms. But the regular terms cannot give rise to a pole, so they are irrelevant. Okay? Let us continue. Now, how do we evaluate this? All we have to do is, you see, we're doing this around the point W. Okay? We're doing this around the point W. All we have to do is to take this object and expand it in a Taylor series expansion around W. Okay? And keep enough terms so that each of these guys give you exactly a pole. Okay? Let's do the easiest term first. This guy is already a pole. So for that, you just keep z to the power, you just replace that by w to the appropriate power. Okay? So the third term just gives you w to the power n plus m plus 2, w to the power n plus 2, del w p of w. With a 2 pi I. Okay, now in every place what we will do is pick up residues. We'll always have 2 pi I, which means we knock off one of these 2 pi i's. Okay? So my accounting for 2 pi i's means we have 1 over 2 pi I square. Then we always use Cauchy's theorem. So we get 2 pi I from that. So every answer we get will be proportional to 1 over 2 pi I. Okay, with that understanding, I'm just throwing away the 1 over 2 pi i's. Final answer we'll keep 1 over 2 pi. Okay, so that's great. So we get first term, I'm just writing it down here, is w to the power n plus m plus 2 del w of t. We'll worry about how it combines what it means in a minute. What about the next? There was this guy. Okay, to get this guy, we need to Taylor expand this once. Okay? So can you see what we will get is plus n times w to the power n plus m plus 1 integral dw t of w. Except there's a factor of 2 because there's a 2.
N plus 1.
N plus 1. N plus 1. Thank you. Thank you. Yes. And everything here comes below del 2 pi I as we pointed out. Finally, there is this character. For him, we have to expand 3 times. Okay? So you get plus n plus 1 into n minus 1 times, now what is the integral here? Here we've got an integral, of course we get c by d. And then we get the integral w to the power m plus n minus 1 with no operator. All with the 1 over 2 pi i's hanging around. Is this clear? 1 by? 1 by 6. Yes. Sorry, thank you for that. 1 by 6 by 2. Okay? Now, integrals over w to some power times t is an L. We've got w to some power times derivative of t. So we integrate by parts. So we get 1 by 2 pi I integral. We integrate by parts. What do we get? We get this guy. This number appears with a negative sign. So we have 2n plus 1. We'll have minus n minus m minus 2. So that becomes n minus m n minus m integral w to the power n plus m plus 1 t of w. These two combine to that. Okay, plus c by 12 into, now what happens with this integral? What's the answer to that integral? Delta of m plus n. You see, powers integrate to 0 unless the power happens to be 1 over z. Cauchy's theorem. Okay, so only if n plus n is equal to 0, we get any n. So this is delta of m plus n. And then we write this as n into n square minus 1. Okay, but now this.
I missed the first line. So completely combined.
Okay, and by the way, this is the 1 by 2 pi I is here. This, the 1 by 2 pi I is equal to delta of n plus n, because that's what you say. How do I combine the two? Here, I integrate by parts. Del W hits this guy. When it hits this guy, when it hits this guy, it makes the power the same as this. But it picks up a factor. Factor is n plus 2. The factor here with a minus n. The factor here was with a plus was 2n plus 1. So n minus of n plus 2 plus 2n plus 1 was n minus. Yes, we'll write this n minus m 1 by 2 pi. Now, if any of you were wondering, are we allowed to integrate operators by parts? The answer to that question is you're always allowed to integrate functions by parts. And we're only talking about correlation functions. I emphasize this many times because it's the source of much confusion. Okay. OPs are statements about correlation functions. Correlation functions are functions. Okay. Fine. What is this equal to? What is this object equal to? So now our final conclusion. L of n, that's L of n, is equal to L m plus n plus c by 12 delta n minus m L m plus n plus c by 12 delta of n plus m into 0 into n squared minus 1 into n. This is a beautiful statement. If I got it right, it's called the Beer statement. Fine. Okay.
So this commutator is also within the correlation.
Yes. What does commutator mean? It means doing the correlator including this contour integral minus the correlator the contour integral will, it means exactly this manipulation of contour integrals within correlation. Always.
So this residue actually cancels 1
over 2 pi, and the remaining 1 over 2 pi is in the definition of LM. You see, T expanded in terms of LMs had no 1 over 2 pi. When you want to invert that relation, Cauchy's theorem gives you the formula. If you flip your notes back, you'll have that formula.
No, what I'm saying is you start with 2L, so you have 2 factors of 1 over 2 pi. The residue gives you 1
over 2 pi, so we had a remaining 1 over 2 pi.
Yes.
That remaining 1 over 2 pi here goes into the definition of this LM plus n.
Second integration was.
And the second integration gave 2 pi I times delta function. That's Cauchy's theorem.
One small question, when you do integration by part, so it generates some boundary terms.
So the bound, we are doing a closed contours. There's no boundary. We're doing a contour integral over a closed contour. Is this totally clear? Any other questions, comments? 100% clear?
So, as far as I know, this is also true as an operator statement, right?
Yes.
So, when can you take OPEs to operator statements?
Yeah, you see, this, once you have proved it, it is an operator statement because it's true within every correlation function. Okay, now, why do I keep saying things like, this is true within correlators. When should you take that seriously? There are two things about that statement that one should take seriously. Firstly, most of the equations we write down are true within correlators. Okay? Provided those correlators do not have other operators coincident with your operator. Okay? Now this is a general fact. Actually, many of the things that we're talking about are operator statements. But it's a general fact that operator statements translate into statements about correlation functions up to terms when operators coincide. Let us take a minute, since this question has come up, to try to understand that. Okay, let us take a minute, since this question has come up, to try to understand that. Let's go back to our one identities. Okay. Do you remember that what we had was an equation like del mu j mu O in the unprocessed form before we turned it into contour integrals was equal to plus delta O1 O2 delta O1 O2 plus O1 delta O2, and this, if this was inserted as W and this is W1 Wn, this came with a delta function. This came with a delta W minus W2. Remember, this was the form of a what. What is a what identity? What identity, as we derive it, is a statement about relations between correlation functions. Now, you could ask the question, what operator statement does this correspond to? Does this correspond to the statement that del mu j mu is equal to delta O1 plus delta O2? Makes no sense, right? Because that depends on what other operators you've inserted. It's not even a candidate statement. It makes no sense. Okay? In fact, it corresponds to the operator statement del mu j mu is equal to 0. That is the correct operator statement. Okay? How does the operator statement, which is true as an operator statement, translate into this computation function? Given that this was the right operator statement, why isn't it true that del mu, j mu within correlators is just 0? Should you get 0 if you put 0 some? I mean, shouldn't that be the easiest thing to deduce? Can somebody tell me what is my fallacy? What is the fallacy in my reason?
To integrate operator.
Say that again, sorry.
So in the statement of the correlation, you're integrating over, like you're integrating over all space. Right?
Why am I integrating? This finally to the local side. This was W. This was W1.
Because element chain equal to 0 is like correlation function equal to 0.
What?
The 1 point function.
Yes, the 1 point function was 0, but if an operator is 0, you would think that times anything else is also 0. This is a word identity, but it's a name.
Time ordering.
Time ordering, exactly. The point is that these guys are in operator form. In the path integral, they just path integral. But in operator formalism, what do they translate to? They translate to time ordered insertions of operators. Okay? So if you want to write this as an expectation value of operators, this is a time ordered insertion of operators. Now time ordered insertions of operators have theta functions. So let's look at this term. Let's forget all the others. They'll all be the same. Let's look at this term. Okay? What is this term? Firstly, because this is statement about correlators. In correlators are functions, so we just take the derivative out. Okay? So we got the derivative out here. Then what was this? This guy was insertion of these operators, but plus a theta function. J times O1 with one theta function. And O1 times J with the other theta function. Okay? So what we're computing is del mu of J mu W O of W1. Now it's to the left if it's later. So theta of W0 minus W1 plus J. I'm assuming both operators goes on it. W1 J mu W theta of W1 sorry 1 theta W1 0 minus W2. Okay. The path integral, the correlation function, the path integral, the manipulations that we did correspond to computing this thing in operator language. Now this del mu can act on the J mu, in which case you get 0. Because del mu J mu is an operator, 0 is an operator. But it can also act on the theta function, in which case you get a delta function in time. But if you see, because you had two things here, this guy will give you one delta function, this will give you the negative delta function. Okay, because it's theta the other way around. So you get delta function multiplying a commutator. Delta function multiplying a commutator of J mu with operator. And in fact, the statement that we have derived so beautifully using our path integral manipulations about the commutator of a J with an operator generating the transformation. In operator language is the statement that J0, by the way, only J0 appears because the derivative acts on theta function, so it's only mu equals 0 to now. J0, commutator with any operator, is local in space, so it gives you the space delta function, times the change in that operator. Because that's what J0 is, the generator of the symmetry. Okay? So, that remaining piece gives you precisely this. The full delta function which came from the delta function in time, times the delta function in space, times the change in the operator. Do you understand? So, this is the thing to be careful about. This is the thing to be careful about in translating between operator statements and statements about correlation functions. Okay? Many of the statements that we make have a direct translation to statements about operators. But this translation is not sometimes immediate, as we've seen. For reasons like this. You just keep your wits about you and you always translate to a particular operator. Is this clear? Okay, great. Excellent. Other questions or comments? Okay, fine. So now that we understand the Veerathura algebra so beautifully, okay, there are one or two small manipulations.
If this was a function, you're saying that this would have been 0 only because you would not have had a commutator between j and o, which gives you the right hand side.
Yeah, what I'm saying is that you might naively have thought that because del mu j is 0, all its insertions are 0,
Yes.
and that you would have got 0.
Yes.
That's not true.
That's not
not true.
If it was a just function.
This would have been true if...
I mean, it's got time ordering only because it's an operator.
I suppose you can say that. I suppose you can say that. I'm just, yeah. Oh, we've seen what the correct statement is this one. And we've seen it from 2 points of view. A, from the path integral manipulations which we worked out, which gave us. B, from operator reasoning, which started with the operator statement del b j b equals 0. These two both consistently get the same answer, but yeah, there was some work between them.
I could do it slightly differently. Instead of doing the del mu in the beginning, I could keep it there, and then it's giving you 0.
But sorry.
Instead of pulling out the del mu in the beginning and then putting in the
You're saying that there is no such. You see, what was the statement here? The statement was about a path integral, right? What was this here? That this is equal to 0 is about insertions inside a path integral. Now, what do insertions inside a path integral mean? Okay, suppose I insert phi of x1. I insert the derivative of x inside the path integral. Okay, if I insert phi of x1 minus x1 plus epsilon minus phi of x1 over epsilon inside the path integral. That is the same as the path integral with the insertion of phi of x1 minus the path integral with the insertion of phi of x1 plus epsilon minus the path integral with the insertion of phi of x1 divided by epsilon. Okay? So within path integrals, derivatives, okay, are always outside. Because what you are doing is this. This is the thing that you're computing. So when you take a derivative like this, it's always outside. Okay, path integral with this derivative always means outside into expectation values. Okay, it's not like there are two separate things you can do within a path integral. This is always the right thing to do. Okay, it's just a matter of bad notation to put the del inside. Okay.
So I can always use the other insertion points are not coincident.
If there are other insertion points are not coincident, these are equivalent. Okay, but when they are coincident, this is what you mean. It's because you're doing it. You know what are you doing? You're computing the path integral with a derivative. What is the derivative? It's the difference between two operators. Okay, you're computing one path integral, another path integral, and subtract. So you're taking the difference between two path integrals. So you're taking the derivative of the path integral. So you're taking the derivative of the correlator. That's always what is meant. Do you understand? Okay? That's what you do with path integrals, and then it is up to you later on to translate what you're doing to operator. Okay? But it's always a derivative of time operator things. That's always a method. Okay, good. But all excellent questions. Though it's not like we're moving like Superman. But that's okay. Excellent. Any other questions or comments? Okay. There is one quick algebraic manipulation I wanted to do for you before turning to derive the Virasoro algebra for the theory that will be of one of the theories that will be very interesting for us. Namely, the theory of reversals. Okay, I want to derive one consequence. Okay, you see, this Virasoro algebra has an interesting structure. Commutators of L's give you L's. That's sort of like you have in a Lie algebra. But only also gives you ones. Algebras in which you've got linear combination of your generators plus 1 called algebras of the central extension. Okay? It's perfectly consistent with a Maisel-Jacobi identity. Nothing wrong with it. It includes, it's just like one of the generators in the theory is 1, is identity. Okay? So what are the combination relations of identity with anything? Well, identity commutes with everything. So we don't bother to write them. Okay, but it's one of the generators. Just an ordinary Lie algebra. So it's one of the generators in identity. Okay? Now, you can ask, is there some sub-algebra of this algebra which does not involve this sort of irritating identity? And you notice here that this appears with n times n square minus 1. So, anything involving n equals 0 or n equals plus minus 1 cannot involve identity. So, there is a sub-algebra here which is made up of L0, L1, L minus 1. Okay? L0, L1, L minus 1, that does not involve, yes please. That does not involve identity. This sub-algebra is sub-algebra of SL2R. Okay? Its combination relations you can easily write down and check for yourself. This is the generator of SL2. SL2R is SL2R, we've got SL2R on the left, we also have an L bar sector. So SL2R times SL2R is what's called the global part of the conformal algebra, conformal symmetric group, and is the analog of what is preserved in higher dimensions. In higher dimensional conformal field theories, in every dimension, in D dimension, you preserve the algebra SO2 D, 2. Okay? D equals 2, this amounts to SO2, 2. And just like SO4 happens to be the same thing as SU2 times SU2. SO2, 2 happens to be the same thing as SL2R times SL. Okay? By conformal symmetry in high dimensional theories. Okay? Again, we will come back to these statements again and again. Okay. Before we have not finished our analysis of the general consequences of conformal symmetry. But before turning to that analysis in great detail, it's useful to look at one example.
The left-hand side is the Euclidean guide. Lorentzian guide is the left side, and the Euclidean guide.
Oh, sorry, it's a question again.
SO22 is what you would find in the Lorentzian guide.
Well, SO22 is what you find in the Lorentzian thing. Yes, everything is Lorentzian. You see, our reality properties of all charges were you see how Lorentzian and Euclidean signatures differ? Only by reality properties. So how does SOD, 1? Sorry, how does Lorentz group differ from the Euclidean group? Only by taking some generators and putting an I. Okay? So, at the purely group, in the purely algebra level, people who are willing to take their generators and multiply by arbitrary complex numbers, it is the same group, the same Lie algebra. It's only a question of reality properties. Okay? Once you've got an algebra plus reality properties, you specify whether you've got SOD or SOD, 1, where D minus 1, 1. Now, what reality properties did we have for LNs? We'll see this more clearly when we look at our example. But we already saw one example. What reality properties did we have for our harmonic oscillator alphas? Do you remember? Let me remind you of this. you remember that we had our expansion, x is equal to sum over I. Somebody may have to help me. I by m alpha m z to the power m. Somebody help me here. It was z to the power m or divided by z to the power m. Anyway, the main point will not get there. I by m z to the power m. Yes, plus the anti-analytic part. Okay. Plus I by m alpha bar z bar to the power m. Something like this. Okay? Now, if we took this expansion and demanded reality in Euclidean space, what would we say? We would say that alpha m and alpha bar m were complex functions. Okay. If we demanded reality in Lorentzian space before doing the analytic calculation, what did we get? We got alpha m and alpha minus m were complex functions. So the difference between, there'll be a similar statement here. When we have P of z is equal to sum over m lm by z to the power m plus 2, and P bar of z bar is equal to sum over m bar lm bar by z m plus 2. If you were directly in Euclidean space and demanded that P plus P bar was a real operator, you would say ln is complex order of lm bar. But what if we worked in Lorentzian space? What if we went back to the cylinder, recontinued to Lorentzian time, and asked for reality? What will we get? We will simply get that Lm and L minus M are complex functions. And that is the reality condition we are always going to impose. Lm and L is L minus M tangent. Because of that, we will always land with the Lorentzian algebras. There's no importance in Euclidean algebra. The Lorentzian algebras are physical. Euclidean space is a trick to do calculations. Lorentzian space is where we move. Okay. Okay, excellent. Yeah. So, but before going on to derive more abstract things about this beautiful Virasor algebra, it's of course nice to have one example. So we are going to dedicate the next 30-40 minutes to the careful study of the free boson. Okay. The main thing that we have to understand when we're looking at the free boson conformity theory, that's not immediate from what we've already understood, is what we mean by composite operators. Okay. So let me take a minute to give you a minute of general thinking. In a quantum field theory, we've been talking so far about arbitrary insertions inside path integrals and so on. And if we were in a lattice, if we had regulated everything on a lattice, everything we would say would be very precise. But there may be issues with the continuum limit. Okay? And one of the issues all of you know about. It's the issue that when you take two operators together, there are divergences. We've been studying some of these divergences, right? We studied it when we computed the propagator of the x's, and we studied it with just now when we looked at OPs and so on. Well, I mean, you may be thinking, well, so what? There are divergences, that's a feature, not a bug. Right about that. However, these divergences have to be dealt with when we are trying to define composite operators. What do I mean by that? Suppose I want to define the operator x squared, the insertion within the path there, of x squared of w. Okay? I could try to define it in the following way. I could define it in the limit as following. Limit epsilon goes to w. Epsilon goes to 0. X of w plus epsilon x of w. So whenever I have the insertion of x square of w, I could mean the following. Except that thing is no meaning. Because even if there were no other operator insertions, we know what the answer to this is. It's proportional to log of epsilon. And the limit epsilon goes to 0. It's divergent. Okay? So by x, if this is what I mean by x squared of w, what I mean by x squared of w is infinity. It's not a very useful thing to call x squared. Okay? This is not what I mean by x squared of w when I talk about composite operators and quantum physics. I mean something else. Now what do I mean? In our simple, free, usually people regulate these operators using dimension regularization. Okay? And that understanding what that means is always very difficult. It's always very difficult to understand physically what dimension regularization means. Okay? But in our simple, free scalar field theory, we will use a much simpler regulator. Okay? We have to define our operators. We're free to do it how we want. We're going to define the operator in the following. To define x squared w, what we will mean is the following. We will define it as limit epsilon goes to 0 of x of w plus epsilon of x of w minus expectation value of x of w plus epsilon x of w. The expectation value, you know what it means, right? It's expectation value within the boundary, nothing else inside. Okay? Now, for 2-point functions.
So that's expectation into identity.
Into identity, right?
This is some kind of contact.
It's subtracting, exactly. It's subtracting the divergent, exactly. Yeah. It's subtracting, really speaking, the operator product expansion, except that these are not quite operators. But morally speaking, the operator product expansion between these has identity with a certain piece. We subtract out the identity piece of the OP. Whatever remains is what we're defining by this operator. There were some other questions. Okay. Now that's great. Okay. So this is x squared. We will sometimes write normal order. We sometimes use the symbol to remind ourselves that we're not just putting x squared of w say at the parenthetical. We're doing this funny operation. Actually, this Pulczynski calls this conformal normal order to distinguish it from harmonic oscillator normal order, which for the particular case of the free boson happens to be the same thing. Provided you give a certain you see, harmonic oscillator normal ordering for the free boson is a bit ambiguous, because while it gives you a clear ordering of a harmonic oscillator A's and A daggers, it doesn't give you a clear ordering between x0 and p, because the free boson has 0 mode sector. The 0 mode sector is not a harmonic oscillator. Okay, so provided you fix on a particular ordering between x0 and p, as we can see, this thing in operator language is the same thing as ordinary normal order. However, we will use it generally for more complicated theories as we will go along, in which case it will differ more significantly from ordinary operator, harmonic oscillator, or normal ordering. We do not care about that. This is some way of defining an operator. This is our definition. This is what we mean by insertions of operators. We insert this object, we subtract the insertion of this object. That's what we insert. Okay? Go on.
It's just a comment. While we are subtracting out the divergences, we haven't subtracted out all the divergences, just the one that was troubling us.
Well, we're going to, in the particular case of two guys, and there is no other divergence. Okay? Basically because we have a free theory. Okay? Because it's a free theory. But hang on for 5 minutes. There will be further divergence, more complicated operators even, and we'll subtract more. That's the point. We want something to be finite. Okay? Now, but along the lines of your comment, some of you are thinking, great, so you've got away by defining x squared, but the square is not the only function in the world. There's cube, there's 4, what about those? how are we going to define x cubed?
We can have composite operators of two different operators.
Two different operators. But let's deal with the free boson theory, in which everything is made out of x. Okay? So let's specify to this theory for a while before getting more ambitious. Okay? Now what will you think? You say that it was limit of epsilon 1, epsilon. Let's say limit all points come together. Okay? Because it will be increasingly composite right now. So limit all together x of all tending to w. So w1, x of w2, x of w3, all points going towards w. But now, this guy can have various divergences. It could have a divergence when w1 goes to w2. It could have a divergence when w2 goes to w3. It could have a divergence when w1 goes to w3. Okay? The way we're going to define this is as follows. We're going to define this as this normal order is equal to is equal to this pure insertion minus expectation value x of w1, x of w2, x of w3 minus expectation value x of w1, x of w3, x of w2 minus expectation value x of w2, x of w3, x of w1. Okay? That's how we're going to define normal order x cubed. In general, suppose we have normal order x to the 4, what will we define it as? The bare insertion minus insertions with any one pair contracted away and all the others left behind, minus insertions with all possible combinations of two pairs contracted away. Okay.
And one more term missing, right? All three come together at the same time.
All three come together? No, that's fine. There's no further divergence. This is our definition. You just remove, you do subtractions or contractions in pairs. It's basically, hang on 2 minutes, you'll see the statement. Okay, this is our definition. For x to the 4, you remove all possible contractions in pairs. Okay? You remove one contraction term, then 2 x's hang out. You have many ways of choosing which guys to contract, which guys to leave. Then you remove 2 contraction terms. Again, you've got several ways of choosing which pairs to contract. And then what's left behind is identity. Okay? For x to the 6, you will also have to remove 3 contractions. You'll have to remove 1 contraction terms, 2 contraction terms, and 3 contraction terms. In every possible pair. That's our definition. Now, what is the claim? The claim is that once we have done this definition, we will have removed all divergences. Okay? Once we have done this definition, we will have removed all divergences. In fact, okay, that we will have defined an insertion that is entirely free of divergences. Okay? In fact, some of you already know this for normal order contractions. This is known as Week's theorem. Okay? Suppose you've got an operator that is not normal ordered, and you want to re-express it in terms of normal order it is. Yeah, some operation that is very similar to this does the re-expressing. And once you have expressed everything in terms of normal ordered, the normal ordered guys are divergence free. Okay? So, the claim is, and we will see many examples of this, we will also understand in generality why it's the case. The claim is that once we have done this operation, our insertions will be entirely free of divergences. Okay? That our insertions will be entirely well defined. So this defines normal ordering. In general, we've got a product of operators. This we'll be mostly interested in this in the limit of W1, W2, W3 come together. But in general, we've got a product of operators. We define the operation, normal order product of operators, by this sequence of steps.
And there are no factors behind those.
No factors. No factors.
No overcompensation.
No overcompensating factors at all. In fact, yeah. This is our definition of normal.
Sir?
Yes.
Can this also be proved like this theorem is proved with induction?
Can this be proved by induction? Well, we have to say what is proved. That there are no further divergences. Yes, presumably you could prove, make an inductive proof. Well, I'll give you a proof, which is sort of. Yeah. Now, okay. This is what we. Okay, this is so far our definition of normal ordering. Okay. Let's proceed with this definition. Let's proceed with this definition to do some actual calculations, and then I'll return to prove some formal properties about this definition. Good things.
Higher order composite operators, you always separate pairs of products of operators in this fashion.
In this fashion, it's basically because we're dealing with a free theory. In a free theory, correlation functions. What we're using is the fact that correlation functions can be Gaussian integrals, obey Wick's theorem. Okay, that's what we're using. Do you know what I mean? What I mean is this. Let's suppose you've got a bunch of guys, right? A bunch of x's. Let me tell you the intuition behind why you will get everything right. Suppose I've got a bunch of insertions, some x to the power m, x to the power n, and x to the power j at different points. Okay. Now, as far as we're concerned, the free theory is a Gaussian integral. So what we're doing here is some integral of the form xi mij xj by 2. And what we're doing, so let's say the different points are the different ij's. So you've got some xi to the power m, xj to the power n, x k to the power b. Thank you. Let's make it 4. I, j, k, l to the power q. This is the kind of correlation function we complete. Now, it is a simple fact about Gaussian integration that all of you probably know. Okay, that this correlation function is simply equal to the correlation function that you get by pairwise contracting all of these x's in every possible order. This all of you know this, right? Simple fact about Gaussian integration. If Wick had been thinking in Feynman's language, he would have had much simpler proof of this thing. It's just a statement about Gaussian integration. Okay? Now, what is the point? What are the contractions? The contractions are the 2-point functions that we've already computed between x and x. Okay? And 2-point functions between correlators and different points are just exactly the same. Are just exactly fine. I mean, there's no problem with it. The only problem occurs because you have contractions between x's at the same point. That gives you divergences. So what you need to do is to have a rule such that once you've defined a subtracted product, you do not allow contractions between the same point. Okay? And the rule for our normal ordering, okay? Our rule for normal ordering, I gave you the rule. I'm sorry. I gave you the rule the other way around. I'm sorry, I'm very sorry. I gave you on the left hand side the normal order, and on the right hand side the actual thing, right? It was the other way. I'm sorry. Please, I have to modify my rule for normal order. Sorry. I told you that we had x. Let me give you a rule. Let me give you the rule again. For the 2-point function, it was okay because only one. Let me give you the rule again, please. I'm sorry. Let me give you the rule again. It's that x can be expanded in terms of normal order. Okay. So sorry about this. Let me work out. Let me give you the rule for normal ordering. Okay. Let me give you the rule for normal ordering once again. Sorry about this. Suppose you have insertions of x1, w1, w2, w3, and w4. Okay. I'm going to define normal ordering by telling you how any insertion can be written in terms of normal ordered insertions. Okay, so first let's do it for 2. Maybe I should. I'll just finish the statement. The statement is that the rule for normal ordering is defined so that if you put just normal ordered operators here, okay, then if you put just normal ordered operators here, then what you're doing is getting the same Wick rule, except you will not allow self-contractions. Okay? So, when you put normal ordered operators here, the normal order sign, okay, that symbol subtracts away all the self-contractions. So the rule for the contractions for normal ordered operators, as we will show, will be just, all cross contractions but not within a group. Okay? So that is the basic idea of the normal order definition. Okay, let me tell you my definition again. I'm sorry. I messed up on my original statement of the definition. I'm going to give you the definition. Okay, let's start again with xw1, xw2. This is equal to normal order xw1, xw2, okay, plus 2-point function of xw1, xw2. Okay, this is the same as what I told you at quadratic. Actually, even on cubic order, it will be the same. But it's the other way around. It's not an expansion of this guy in terms of those recursive. It's this way. Okay, it's xw1, xw2, xw3 is equal to normal order insertion, okay, plus xw1, xw2, xw. Okay, plus the other. Again, this is the same as what I told you about at cubic order. But at quadratic order, different. I suppose it differs. Okay? It's xw1, xw2, xw3, xw4.
All the uncontracted guys will be normal order.
All the uncontracted guys are normal order, exactly. Okay? Are equal to, well, there's one term which everything is normal order. Plus, there are terms where two guys are not normal order and 2 guys are contracted. Plus, there are terms where there are all the contractions. Okay? Now, if you want to find what this 4th order guy is, in terms of the abnormal order guys, one way to do this is to solve these relations. Okay, it will basically be the same thing, except that in going from one, here we had all plus signs. In inverting, we have alternating plus and minus signs. Okay, but this is the clear definition. This is my definition. I'm sorry I messed up. Is this clear? Any confusions about this? Sorry about that. Okay, so we will come back, perhaps even at the end of this class, to study formal properties of this normal ordering operation, prove lack of divergences, things like that. But before doing that,
how would you define a normal order in this sense?
Yes.
In the sense that
suppose I want normal order of this.
Yeah, I mean, what would you mean by normal order? Generally, when you do Higgs contraction in case of harmonic oscillator, you mean that you want the A diagonals to be on the length side of the
All I'm doing is defining insertions within a path diagram.
Yeah, so the motive would still be removal of divergence.
Yes.
That's what you mean by normal order.
What I mean by normal ordering is, I have to tell you what insertion I'm putting. So I'll give you some linear combination of bare insertions. That will define my normal order insertion of whatever. It's true, the motivation is removal of divergence. But this is the definition. I have to put something inside a path diagram. I'm telling you what I'm putting. That is my symbol. That thing is defined so as to remove divergences. Okay? It will obey many nice properties, as we'll see. And will almost coincide with your ordinary normal. Yes, please go. Ordinary normal. You see, in this theory, this will be almost the same definition, up to some convention regarding zeros. Okay? But it is a definition that we can usefully employ for many free conformal field theories, where it will often differ from traditional normal orders. Okay? Hang on for probably to the next class to see examples of that. Okay? Okay? Yeah, hang on. Okay. Now that we know what we mean by composite operators. Okay. Now that we know what we mean by composite operators. Okay. Now that we know what we mean by composite operators, we're ready to deal with the full with our free boson theory in full generality. So let's start doing this even before we come to understand more systematically what this normal operator is. Okay. The first thing we're going to do is to take our expansion of the free boson, and we have this expansion of the X field. That expansion, if we followed conventions nicely, should work out to the same thing as del X is equal to alpha n divided by z to the power n. Is that an I difference? First, let me just check. This is just. It's probably an I. Just hang on. It's hard to find anything. Is he has minus I square root alpha prime by 2 2 will be okay, this is what he has. No. Yeah, okay. Somebody just remind me of our expansion and we'll make contact. Somebody remind me. X was equal to?
X0 plus alpha prime b tau plus some sigma summation over n I alpha n over n e to the power, sorry, this is z to the power minus should be minus n here.
Over z to the power n?
Yes.
Good.
Should be and the constant
Plus. Okay, what about alpha? Are the alpha prime matrix?
Yeah. The square root of alpha prime matrix.
There was a square root of alpha prime matrix. Okay. So this agrees exactly. Now if we differentiate.
Yes.
So this works, right? Because now if we differentiate, we get a factor of minus n, which will give us minus n. Okay? So this agrees exactly with this nice definition now, but except we have to figure out what alpha 0 is. Okay? So this fellow here was alpha prime p into was this tau Euclidean, please?
No,
This was tau Lorentzian. So tau Lorentzian was minus
I times tau Euclidean.
plus tau, but yes, tau Lorentzian.
Lorentzian is I minus I.
Well, I into v of x into minus v of x dt has to turn out to be negative. So, no, you're right, minus I. So tau Lorentzian was minus I tau Euclidean. We get a minus I tau Euclidean here, which is sigma 2. I'm sorry, somebody also have to help me. Z was equal to sigma 1 plus I sigma 2, and Z bar was equal to sigma 1 minus I sigma 2.
No, exponential.
No, exponential.
No, sorry, right.
This is
W. Yeah.
It's a long term.
It's a long term. I'm sorry, we just get this totally straight once and for all. Sorry. So, somebody help me with Z and.
It was alpha dash by 2 p into W bar minus.
Wait, this guy here was the time of W, right? Okay, so this guy was sigma 2. This guy was sigma 2, and now we want to know what Z is in terms of sigma 1 and sigma 2. Okay, so please help me. What was Z in terms of sigma 1, sigma 2? Does somebody have their notes? It was e to the power sigma 2 plus or minus I sigma 1? Minus I sigma 1. Wonderful. So, Z bar is e to the power 2 sigma 2. So, 2 sigma 2 is equal to half, so 2 sigma 2 is equal to half log Z bar. Okay. So this expansion can be written as x naught minus I alpha prime by 2 log z bar and P plus square root alpha prime by 2 I alpha n by n zn. Okay? And, okay, we'll go quickly over this. So this is this expansion. And now, if we take this and we differentiate it, okay, the first term, let's just take the analytic pieces. The first term will give us minus I alpha prime by 2 P by Z. Okay, this is to be compared with this guy. And so we conclude that alpha 0 is equal to square root of alpha prime by 2 times P.
This alpha 0 is not the same as the original.
What was our original alpha 0?
There was not.
There was no alpha 0. Okay, so I will check that Wilczynski has the same. Wonderful, it's correct. Square root of 2. Alpha 0 is right, it's square root of alpha prime by 2 into momentum. Okay, absolutely right. No issue. Okay, so if we make the following definition, alpha 0 is square root of alpha prime by 2 p. What is the alpha 0 bar? Will also be square root of alpha prime by 2 p. So it's only 1 p. Came from the same place. This is basically the lack of factorization of the free boson between left and right modes. The zero mode couples the two. Okay, apart from that, the free boson basically factorizes between left and right modes, except for the zero. Okay, so X has this expansion with these funny factors of n, and with the funny factors of n and this funny factor of log. Okay. But all of the funniness goes away in X. Okay? So the best way to remember the mode expansion, or to think of the mode expansion, the free boson, okay, is in terms of del X. In terms of the field del X, all of the oscillators are coefficients of nice pole-like singularities. Okay? So, just like we did for the Virasoro algebra, we can now just like we did for the Virasoro algebra, okay, just like we did for the Virasoro algebra, we can now actually look at these alpha n's as charges for some currents. Okay? In order to make that precise, what we do is to solve for this relationship. Okay? Alpha n is equal to the integral of 1 over 2 pi I and then these horrible other factors. Square root 2 pi alpha prime and then goes plus I times 1 by 2 pi I times integral del x z to the power n dz is alpha. So you see, what we've got in this theory of free bosons is that we've got a bunch of currents. These currents, the expressions for these currents are simply del x z to the power n. Okay? Why are these currents conserved? Simply because del x is holomorphic. By the equation of motion for x, del power of del x was 0. Therefore, del x was holomorphic. Therefore, del x times any holomorphic term like z to the power n is nice and conserved. Okay? So we've got alpha n's can be thought of as currents fields corresponding to some strange holomorphic currents. Sorry, charges corresponding to some strange holomorphic currents. The operator algebra between alpha ends can now be deduced from the OPs between these currents. Okay? So suppose we wanted to compute alpha n, alpha m. Okay? Suppose we wanted to compute alpha n, alpha n. Firstly, we get two factors of this ugly factor. Two copies of this ugly factor. Okay? We get minus 2 by alpha. Then what will we get? We will have two factors of 1 over 2 pi I. These 1 over 2 pi i's will go away. First one will go away when we take a residue, and second one will go away when we get a delta function. Okay? I'm not keeping the 2 pi i's around, those will put out. Okay. So what remains is this, right? It's the residue between del x at z, del x at w. Whatever we get for the residue of this, and then integrated dw with the 1 by 2 pi. That will be our final answer. This clear? Okay? Now, we had that x of z, and we have z to the power z to the power n, w to the power. Okay, now we had z of x, z of w. We had z of x, z of w was equal to, you remember the 2 pi function, was equal to minus alpha prime by 2 log of z minus w, z bar minus w bar. What is this translated to for del x? Just differentiate both of these. Right? The first derivative brings it down 1 over z minus w. Okay? And the second derivative makes it minus 1 over z minus w squared, except that it's a derivative with respect to w. So it becomes plus 1 over z minus w squared. Okay? So, del x of z, del x of w is equal to minus alpha prime by 2 1 over z minus w the whole thing squared. Could you check that you believe that? No, the minus sign is correct. So this is just correct. Okay, it looks right. Yes.
I understood when there was a contour interpretation for currents on the right hand side, then you could actually make the two terms into one, with one contour going around at the other point. But in this case,
this is the contour. Right? Alpha n is this contour integral. You want to compute the commutator, you have to do the same moves. One before, one after, one before. Anytime you've got a contour integral, some charge defined by contour integral, you want to compute the commutator, same moves. Okay?
Yes, how does this minus thing goes over?
But
there shouldn't be any percent because one z comes down and another with respect to w that brings down the minus. So it shouldn't be.
no, but then you're also differentiating 1 by z, which has minus 1 by z. So there are two minus signs. Right? Let's say the first derivative with respect to z, so that comes down with no minus. Second derivative is w, there's two minus signs. Okay? So now we want to compute this oscillator algebra. Okay? what we're doing here is a little exercise to try to compute the oscillator algebra, which we already know. We've already computed using canonical quantization, using these fancy contour techniques, just to get used to them. Okay? And then we will use the same techniques, same kind of tricks to do more interesting things. Okay, but let's see that we get the right answer. Okay, so alpha n, alpha minus n. Okay, we had a minus 2 by alpha prime, and then the operator product expansion has 1 over z minus w squared with a minus alpha prime by 2. So these two factors cancel each other. Okay, so this is equal to integral what we get from residue of, now there's only one singularity. Okay. We get integral residue of z to the power n, w to the power m, 1 over z minus w the whole thing squared. Integrated dz over 2 pi, dw over 2 pi.
But this is minus.
W raised to minus.
You did alpha and alpha minus.
I did alpha and alpha.
No, I mean, you changed it.
If I have, I did.
In this last year.
Where?
Yeah, that's alpha minus.
That's okay. So then this is equal to n times w to the power n plus m minus 1 dw by pi I. Which is equal to n times delta of n plus 2. Do you see how beautifully it's working? Is the algebra clear to everyone? Okay, so the stuff that we got from canonical quantization, we reproduce now using these fancy contour techniques. Okay, and in much of our discussion of string Walshing theory, we will take this as the guiding principle. That is, we will maybe loosely inspired by canonical quantization define various expansions. Then those expansions stand on their own terms. Any algebra between the operators in those expansions, we with our own hands will rederive using contour techniques, just to make sure we haven't made mistakes in analytic delineation, putting eyes. Okay, so if this was the expansion of the harmonic oscillator, it implied that this was the algebra of oscillators. Yeah, we need to go for lunch. Just one, yeah.
Earlier we used OPE between the operators, but this time we are using the expectation again.
Yeah. No, the time we're using expectation, it's a very good question. It's because, I should have said this, it's because of the expansion. The expansion that x is equal to plus normal order. And because I've already told you that the normal order guy has no singularity. Okay? So the OPE here is that we get identity with the singularity plus likeness. That's what this normal ordering stuff told us.
So now we can do this for any such thing that we complete. We can just look at the divergent paths.
We have to keep all divergent paths.
Yeah.
And if we had more than, let's say we had 4 x's here, then we would have to keep the other less singularities. Okay, so last two minutes maybe I mean we have the time. Let me just tell you 2 minutes and then we can do it properly. Okay, now that we got used to manipulating, working with these, with the free boson, we can ask what is the stress tensor of the free boson? Okay, you can derive this. You can derive the stress tensor. You can derive the stress tensor using Noether procedure. Okay, I'll leave that for you as an exercise. It's a simple exercise. Okay, and what you're going to find is that T is equal to, up to some normalization that we have to look up, is del x times del x. T bar will be del bar x times del bar x. We have to look up the normalization. This book is a great book, it's always very hard to find anything else. There's an alpha prime. Minus 1 by alpha. Okay. Canonical quantization gives you T is equal to del x del x. Now del x del x, if it's just taken to be the naive insertion, makes no sense. Yeah. Our definition is going to be T is normal ordered del x del x. Okay. Now that we have this nice definition, we've also worked out the OP between del x and del x. It is now a trivial exercise to work out the TTOP. I'm going to do it for you in 2 minutes. We can redo it at the beginning of next class if you want, where you guys can look at it yourselves. Okay, let me very quickly do this. So we have T of Z, T of W. Okay. First term we get is when we contract between the Z minus W, we contract both pieces. Del x give us what? Minus alpha prime by 2. So first we have minus 1 by alpha prime, so that whole thing is squared. Then we get minus alpha prime by 2, that whole thing is squared. Then we get 1 over Z minus W the whole to the 4. But okay, we have 1 over Z minus W the whole to the 4. But we also get that, there were 2 ways of doing the contractions. There are 2 del x's with W, 2 del x's with Z. We can do the cross contraction 2 different ways. So we get a factor of 2. Okay? So this term, the most singular term, is Z minus W the whole thing to the 4 with a factor of 2 squared times 2. So 2. Remember we decided to write it as C by 2. So this we write as 1 by 2. So C is 1. Okay. What about the other terms? Now you get terms when you contract one of this guy with one of those guys. How many ways are there of doing it? Well, there's 2 ways to choose the first guy to contract and 2 ways to choose the second guy to contract. 4. Okay. So now we get one factor of this. So that's minus alpha prime by 2. 1 over Z minus W the whole thing square. There's the factor of 4 from the number of ways of doing it. Then there's what's left behind. What's left behind is normal order, remember. Normal order of del x of Z, del x of W. Okay? And then plus there's the term where everything's normal. That's regular. So that goes away. Okay? Finally, this guy, within normal ordering is regular, so we can just tail and expand. Okay? So firstly, what is this guy? So far what have we found? We found that T of Z, T of W is equal to 1 by 2 by Z minus W the whole to the 4. Then now the factors of 2 here over 2, right? So plus 2, normal order del x of W, del x of Z by Z minus W the whole thing square. Minus that should have been. Minus that should have been. Why? No, it should have been minus. So I messed up various things. T had a minus 1 by alpha prime. The whole thing.
Yeah, in the second one, that wasn't taken.
That was taken into account, right? In the first time, but in the second time it was not. Yeah. So this has a minus. So 1 by alpha prime. The whole thing squared times minus alpha prime. And I've taken that on the half. So the whole thing is just with a minus 1 by alpha prime, right? minus 1 by alpha prime times 2. Minus 2 by alpha prime is. Okay? Plus regular. But now I take this and expand it in Taylor series expansion in Z minus W. This is T of Z, T of W is equal to half Z minus W the whole thing to the 4. Okay? Minus 2, so plus 2 into del X of W, del X of W, everything is normal. Normal order, okay, by Z minus W into minus 1 by alpha prime. Then minus W squared minus 1 by alpha prime. Okay, and then plus del of del X of W, del X of W by Z minus alpha prime. So Z minus W into minus 1 by alpha prime. What have I done here? Here I Taylor expanded. So I get one factor of del X at W. There's a factor of 2. But then I write that del 2x times del X is half of del X del X. Okay, that's the manipulation I've used here to take the overall derivative outside and to get rid of the factor of 2. But these quantities, minus 1 by alpha prime, del X is T. Okay? And so we concluded that T of Z, T of W is equal to 1 by 2 Z minus W the whole thing form plus 2T of W plus del T of W. Exactly the structure we expect on general grounds, but with one identification. C is equal to 1. Okay. In doing this calculation, I have assumed you know that I have assumed that Wick's theorem applies. Okay, when we have to our definition of normal ordering, which is true, but we will start the next lecture in explaining that and the properties of normal ordering in more systematic detail. Okay. Okay, end of class. Was this calculation clear? Did I go too fast? Yes, I went too fast, or yes, it was clear. I went too fast. We'll start with the calculation again. Okay.